All right, thank you very much. It's great to be here. This is the first time I've ever given a talk at PyData. I'm excited about this topic. I hope you guys find it interesting. It's really powerful, and Python's a great tool to do these sorts of analysis. It's not working. So I put together, there's a little bit of code to talk through an example. It's because of challenges with the Wi-Fi, I wasn't able to upload all the data at this point, but it'll ultimately throw this up there, including the slides. Right now there is a Jupyter notebook if you want to follow along with a little bit more code instead of the pseudocode that are in the slides. So I work for Apollo Agriculture, and Apollo's goal is really just to help smallholder farmers increase their profits. And we do this by, in order to do it at scale, we need to leverage a whole bunch of different technologies, and geospatial data is a core component of that. And so that's really what I want to sort of focus on today. Some of the examples of how we use this. So a big part of it is we need to determine with whom to give a loan for seed and fertilizer for these customers. And we want to try and determine as efficiently as possible who is most likely to pay. And so we use, for credit scoring, we can do things like look at satellite data to look at their house and measure how far their house is from a road, for example, and extract these kinds of features that then we can feed into a credit model. The other thing we can do is we can look at fraud detection. We have a lot of people applying for our loans, and sometimes there's legitimate confusion, but sometimes multiple people will apply for the same piece of land. And so that's one way that we can use GPS data for that when we actually mark a field to make sure we're not giving multiple loans for the same piece of land. The other thing we can do is we can actually do a lot of work to analyze the farms themselves. We send out people to walk around the boundaries of a farm, and then using that combined with time series of satellite imagery, we can measure things like historic yields, or at least estimates of historic yields from the satellite data once we know where their farms are located. And then finally, in order to be as low touch as possible, in order to reach as many of the customers as we want, we send people out, our field agents who have smartphones, and we want to send them to the location of our farmers. And since we're in Kenya, Kenya doesn't really have much in the way of an address system. It's hard to know where people are, and so we use schools as a proxy for that. And so we use this spatial data set of school locations that comes from the Kenyan government in order to then help route our field agents and let them know where they need to go in order to meet the farmers. So these are just sort of some of the examples that we use. For me, I didn't really use spatial data until I started working for Apollo Agriculture. My primary goal in this talk is to try and be the talk that I wish I had had before I started doing this, to give a background of this. No one will become an expert on any of these things in a short talk like this, but hopefully give enough background where you can at least start Googling what you need to know in order to solve your exact problem. I see. Right. Okay. So I think all of these talks need to have at least one webcomic, so here's mine. And I think that sort of leads me to the secondary goal of this talk. The thing about working with geospatial data that's great is it's plentiful and cheap, and there's all sorts of different data sets you can get. The thing that's hard is that when you're dealing with that, it's easy to sort of make spurious and false conclusions, as this person nicely demonstrates for us. And so I want to try and give a little bit of an understanding and tools of how to do a little bit better than this, because when it's done well, you can get incredible value out of geospatial data, but when it's done poorly, well, not so much. So a bit of background. Let's talk about what I actually mean when we talk about geospatial data. Really simply, all it is just data that is referring to a specific location on Earth. And that comes in two different forms. So there's vector data, and vector data are points. So this is something like, if you take a single GPS reading on your phone, that's, the actual single point location. You can get things like lines. So if you look on like OpenStreetMap, and you get, the actual location of a street is defined via a line. Or you can have things like polygons. So when we have our agents walk around the perimeter of a field, that turns into a polygon that is a well-defined, has some area associated with it. And then there's raster data, which really is basically an image. And these sort of come in two different flavors. There's these thematic raster images where the values are discrete. So this will be something like a land use map that'll have, this is a forest, this is farmland, this is a city. Or you can have continuous data. Well, obviously it's not truly continuous since it's an image, but this will be something like your satellite image where you're looking at all the RGB values that you can have. So for vector data, like I said, this is really defining a region in space, and then you attach some properties to it. And so you can use something like a JSON format, and you're just sort of specifying very concretely the coordinates of a location, and then you can add in these properties that are things, anything you want, names, marker sizes, whatever you want to put into that, you can do. The type of data formats you'll see, this is where a shapefile is, if you're coming from sort of the GIS community, that's where you run into. But there's sort of a wide range of formats that you can see. And the sorts of data sources you get, this is how, if you have like survey data from governments or NGOs, they'll often end up as sort of vector data. And here's some libraries that you can use. I'm going to try and make these slides as useful a resource as possible, so I fill them in with a bunch of links, but won't necessarily talk through everything. So this particular data point that we have is actually this approximate location of where we are. This is what I grabbed from the website, so maybe I'm off by a little bit. And so this is how using GeoJSON.io, which is a nice tool to look in and sort of explore your vector data, you can easily plot this point. It's then taking the properties that I defined here in terms of specifying things like the marker, and then throwing it on top of a satellite image of here. And then that satellite image is exactly the next piece of data that we have where we talk about raster data. As I said, it's basically an image. I use scare quotes here because when we talk about images, it's not necessarily RGB values. It's not necessarily just limited to the optical wavelength. So when you deal with satellite imagery, you'll often have lots of data in the infrared and even lower, as that provides more information about things like water or vegetation. So this is one of my favorite visualizations. This is using the infrared along with green in order to figure out where vegetation is. And this is done because the way photosynthesis works, plants want to absorb the green light, but not the infrared light, since that just makes it hot, but isn't energetic enough to do photosynthesis. So you can make these really strong contrasts. And so this shows over the years, on average, where vegetation is across the continent of Africa. And this is exactly the sorts of things that we're interested in Apollo agriculture. The data formats for this are basically just your typical image files, and then you have some metadata attached to it, and you can get this, we use lots of satellite imagery. You can also use things like aerial photography, and then in some cases, things like elevation are actually just more efficient to represent as raster data. This clicker is struggling here. So kind of implicit in this discussion is location, and I think it's really worth spending a little bit of time to talk about location and how we specify it. Really anytime you're talking about it, you always need a coordinate reference system. I mean, this is true whenever you're talking about data that's spatially located. And so here, what I'm kind of showing you is this is an example in a data format about how you're specifying location, and this kind of stuff you see all the time, and it's really confusing and can be really intimidating. And so I kind of want to walk through just a little bit about what we mean here and hopefully sort of demystify this stuff. And the key thing is that because not all data are represented in the same coordinate system, you need to pay attention to this in order to then make comparisons across different data sources. So the main thing is that there's this EPSG, which is like European Petroleum something, and they put together this geotic parameter set, and that's a convenient shorthand that's used to specify these. And so this here is EPSG 4326 is how people refer to it. And that's the specification that's used for your GPS. And so I think we're really used to GPS data. We're used to thinking about it in terms of lat/lon. But I think it's useful to recognize that that is just one coordinate system that's used, and it's not the only one. And so the reason for this is that the Earth is, I don't know, what people probably remember from school, you learn that the Earth isn't actually a sphere, but it's an ellipsoid. That's also not true, right? I mean, this is a really complex body that's actually moving all the time. you have an earthquake and everything shifts. And so there's a series of ways in which we specify the shape of the Earth. And so in order to specify lat long, you need to come up with an approximation for the shape of the Earth. And then on top of it, so normally you approximate this as being something like an ellipsoid, and there are different ellipsoids that are used throughout. A good approximation for the ellipsoid in North America is very different than a good approximation in Australia. And so there are different ellipsoids that are used. And then on top of it, if you want to be really accurate, you need to recognize that there are these lumps throughout. There's inconsistencies in gravitational forces, and so you can specify that in terms of the geoid. All these things get encoded into something like EPSG 4326, and that's sort of what that means. And then the last piece of it is on top of the shape of the Earth, we actually do a bunch of very careful surveys. So I come from the U.S. In the U.S., you see these actual disks mounted. If you go on a hike, you'll see them all the time in stone that is well-surveyed points. And these points form a dense network, and those are the way in which then you interpolate in order to know where things are. And so that gives you sort of the shape of the Earth, the location of the Earth, and then on top of that you have projections. And so that's going from 3 dimensions to 2 dimensions. So datum, that's sort of how you come up with these dense networks. I love this image. This is the careful surveying of the subcontinent of India that happened in the 1800s. I am continuously blown away by the amount of care and dedicated data that happened and was collected in order to understand the shape of the Earth. I think I'm doing okay on time, so I want to tell this really amazing story. These guys were out there in like the 1800s measuring this, and as they got near the Himalayas, they knew that as they were surveying, you want to have a plumb line going straight down when you take your measurements. But they knew that the Himalaya mountains are going to cause gravitation, so their plumb line's not going to go straight to the center of the Earth, but actually be slanted towards the Himalayan mountains. So they were taking into account of that, and they do this whole big arc of series of surveyed points, and they were off by a small amount. And so they were so confident in their data collection that they said, like our calculation for how the mass of the Himalayas is shifting plumb line must be wrong. And the only way they could come up with that was to propose that mountains actually have structure underneath the Earth. So on top of not just seeing the physical mountains that you can see, but there is inconsistencies in the density of the Earth underneath the mountain range. And this is sort of like preliminary data that started leading to theories of plate tectonics. And it just blows my mind that this is what they're figuring out just because of the care of their data collection. So the datum that you use do vary across the Earth. Like I said, the most common is EPSG 4326. That's what you use for GPS. If you're out collecting your own data, it will almost always be in this format. But then once you start combining it with other sources of data, if you grab like government survey data or anything like this, it'll typically not be in that data format. So in North America, you'll see NAD 83. People are really creative with their names. That's the North America Datum 83, meaning it was made originally in 1983. If you're in Europe, you'll see ED 50, European data that started in 1950. These things get continually updated as they both collect more data and taking into account the slow shifts in the locations. And the key thing just to recognize is that if you're looking at one point on the Earth and you're using a different datum, you'll get a slightly different number in terms of lat long. And so you need to take that into account. And then the other thing you have is you have projections. So I think projections are great. It's a lot of fun to nerd out about them. The key thing to recognize is just that every projection leads to some amount of distortion. It's not possible to take a 3-dimensional shape, put it down into 2 dimensions, and not lead to a distortion. And so when you're dealing with this, what you want to do is you want to try and come up with the projection that best matches your use case. And so you often might care about things like area or the shape or direction. Different projections are optimized for those use cases. So here are 2 different projections. A common way to think about distortions is these circles are all the exact same size and shape on Earth, but then when you move into a projection, they change. So in the top left, this is a Mercator projection. And here what happens is we are preserving the shape of a circle, but we lose the size. And so as you get away, you get these distortions of size. I think we're all pretty familiar with this projection. We see it a lot. An alternative projection's on the bottom, and this projection, the shape gets incredibly distorted, but the actual size of these circles are the same. So if you want to do a calculation about the area, so when we're calculating the area of field, for example, we want to work in a projection that where area is conserved or is at least minimally distorted. Common projections you'll see. One of the really common ones is the web Mercator. If you're dealing with any sort of app, this is what you'll probably use. This is what all the web maps use. So if you're using Google, Bing, OpenStreetMap, all of these are using web Mercators. I find it really interesting that actually Microsoft has by far the best documentation I've seen on this. I'm assuming it's because they're trying to recruit people and they need to do it with documentation. But you'll see this all the time. Another really common one is the plat carré, and that's basically just moving lat lon to XY. And so if you see something that's as a map and it's listed as EPSG 4326, that's not technically a projection, but that's just taking the lat lon that's specified and putting it onto XY. And this is really common if you have global raster data. This is actually the format that we'll see in a little bit when I talk about nightlights, and that's the format of this. Two other really interesting ones. The transverse Mercator I use all the time because that's what you see with satellite imagery. The nice thing about these is it's basically the distortion is minimal along a line of longitude. And so that's the path a satellite takes when it's collecting imagery. And so that's why you use this. UTM is a series of transverse Mercators that you'll see a lot of that are basically, I think there's 32 of them that go around the Earth, and those are a way of those are commonly used in satellite imagery. And then finally, there's a whole series of equal area projections that you use all the time if you're calculating area. Okay, so the last thing I'll sort of say, and this is the last sort of theory-ish slide, is that, I hope I didn't bore you too much about this stuff. I hope, that these things are all very, important to keep in mind. But ultimately, what you really end up doing, practically speaking, is you end up doing lots of transformations from one projection to another. I stole this graphic in its just hideous font from Paul Bolstad's book, which is an excellent reference if you guys need to dig more into some of the technical details behind these things. But basically, ultimately, all you're doing is you're going to be moving from one projection to another. And when you do that, you have to go through the geographic projection, meaning the full, three-dimensional. And typically, your software will handle that for you. The reason why I want to show this is just to emphasize that, just going from one projection to another there's no distortion in this process. It's perfect because these are mathematically well defined. If you're going from one datum to another, so these different geographic coordinates, then that is you're using these different interpolation schemes, and so you can actually it can be a little bit of loss in it. You're not necessarily going to be as precise. Generally, your tooling is going to handle this for you, but it's important to know that that's what you're doing. So then finally, what do you actually do when you're dealing with this? I gave you a bunch of theory. Hopefully it wasn't too boring. But really, I sort of think of it as it's the fundamental steps that you do that I find myself doing all the time are really quite simple. You load in some data from some source. Maybe you created this data, or you get it from a survey, from a satellite imagery, whatever it is. You do some sort of transformations on this, and this is sort of the key thing, is that whenever you do these transformations, you basically just want to say if you're combining two different data sources, you need to make sure they're in the same coordinate systems. Sort of general rules of thumb is that you want to transform it into a projection that matches what kind of calculations you want. And then the other rule of thumb is that if you're dealing with vector data and raster data, which is very common, you want to transform the vector data to match the raster data. And the reason for this is that, raster data is an image. If you make a transformation on an image, then you might be splitting a pixel into multiple pixels. And that means that you might have some irreversible processes there. It's not going to be perfect. So as much as you can, you want to sort of treat the raster data as is. People who put together raster data sets that you're working with do a ton of work to try and make it as accurate as possible. And then, you just want to make the transformation to match it. And then once you're done here, once you do your transformations, then you're combining data sets and you're making some calculations. So for example, if you have a polygon, you might use that polygon to mask the raster data and then make some calculations on that. We find ourselves doing intersections of polygons all the time. So for example, you have a field and we want to know sort of, is this field in our service territory, which we define via some polygons, or you want to know sort of what government ward it's in, whether, ward state, that sort of thing. You calculate areas of things. I mean, the sky's the limit once you're in this sort of calculation phase. But this sort of load transform, and then you do some combinations calculations is the general process that you go through. And so here's the tools that I use all the time. Ultimately, there's these low-level tools that are really highly optimized. And typically, the way I do it, I do almost all my calculations in Python, and there's almost a one-to-one mapping of these highly optimized low-level tools within a Python library that wraps around it. I think about this in terms of the types of data structures you have. So if you have vector data, Shapely is the thing that does the actual manipulations of these objects. So if you have polygons, lines, points, then Shapely is the thing that does you're calculating intersections, that sort of thing. And it's sort of unaware of all of the complexities to do with projections and all that stuff. Fiona is a great way of loading data in and out. And PyProj is the way you actually change your projections. On raster data, really the only library I use is raster.io. It kind of does all the things you need in terms of reading it in, and then any sort of calculations using the raster data. And then you can also simply drop into low-level NumPy and do whatever you want. Sort of miscellaneously, GeoPandas is great. It basically extends pandas to allow you to do a lot of the geometric operations. So if you can use it, I recommend it. It kind of gets complex if you're dealing with large data sets since it just reads in everything. So if you're dealing with a really large data set, you might need to be a little bit more careful about how you read it in. But then it supports all of your normal pandas operations, all this very nice row-oriented calculations. And also plotting stuff. So Descartes and Cartopy are the things that I use the most. They're matplotlib based. So you then once you get into that realm, you can do whatever you want with matplotlib as well. Okay, so that's sort of the background things, and now I kind of want to walk through a little bit of an example dealing with nighttime lights and wealth. So to start out with, can anybody name this country? So this is Germany, right? Pretty easy to tell. You see a really nice shape. You can point out all the big cities, the urban areas. Pretty nice. So what about this country? Syria. What was that? Syria? Yeah. So this is Nigeria. It's a lot harder to tell. These areas down here. This is the coastal area and around Lagos. And then up in the north, there's not nearly as much night lights. So you might think I'm choosing a hard one because boundaries are maybe a little bit easier. But if I show a different country, can you guys name this one? Yeah, pretty easy. All right, so here's an in between one. Yeah, Mexico. That's pretty good, right? Okay, so I love dealing with night lights. I think it's a really fascinating data set. And it's because of this sort of interplay between nightlight intensity, human activity, and wealth. So one of the big sources of nightlight data is actually the military. Militaries are super interested in this because of its correlation to nightlight activity. So this data that we get is actually generalized over many, many images in order to remove transient light effects, clouds, things like this. But the military is really the only ones who are collecting this kind of data because most uses of satellite imagery, you don't really want high-resolution nightlight data because there's not a whole lot going on there. You're collecting lots of images of oceans, things like this that aren't that interesting. But the military uses it for things like, are people trying to hide activity in the desert, things like this. So if you are trying to do some covert operations, do it on a cloudy night as well as at night. So what we're going to do, though, is we're going to try and sort of look at night lights and wealth. And so concretely, we're going to look at this demographics and health survey in Nigeria, which is why I was showing you Nigeria to begin with, which is a survey that's done to collect information about all kinds of information. But one of the things we're interested in is sort of assets. This is something we're interested in at Apollo because making calculations on nightlight data is very cheap, and we want to try and find as cheap ways as possible in order to collect data that's meaningful for us because we need to do that in order to serve our customers at scale. And this work is a little bit motivated by this paper in Science, so they did some of this stuff, and it's something that we're quite interested in following up on. Okay, so to just sort of walk through the process of what we're doing, I'm linking this again if you guys are trying to follow along. But basically what we're going to do is we're going to load in some data. So we're going to load in this survey data, which is vector data. We're going to do some amount of sort of poking around, a little exploratory data analysis, some plotting. Then we're going to load in the nightlight data. Similarly, we can kind of explore it a little bit. I already showed you, the payoff a little bit, so unfortunately. And then we want to extract the nightlight intensity for the areas of interest. And then we can make some calculations on that, and then finally we can make some plots. Okay, so this is a fairly standard process here. Okay, so to load in this data, I use GeoPandas because I can get away with it here, and this makes my life a lot easier. So very simple to read in this kind of data, like classic pandas single line load kind of thing, and then we can look at the head, first couple rows. And so what we see here is we see these cluster ID. Because this is survey data, it's somewhat anonymized. There are, I think, about 80,000 rows, but only about 800 clusters, so they anonymize the data a little bit. It has an asset score. And then this is what you see a lot of in Pandas. So this is the geometry. And so the way in which GeoPandas works is it has a special column that does all this sort of geospatial stuff. In this case, it's nicely labeled as geometry. And what's inside here is typically a shapely object. And so these are points. So what we have here is a series of points that were probably collected by somebody using their GPS and then located for these clusters. And then the other thing we want to look at is what is the coordinate reference system. And again, not so surprisingly, we see EPSG 4326, which is why we know it's something like a GPS location. Okay, and now typical exploratory data analysis. So because it's pandas, we can just sort of take advantage of all of the typical pandas functionality. So we can just easily make a histogram of the asset scores. We see that this is some sort of normalized score, centered around 0. And then what's more interesting is then we can kind of try and actually plot the spatial distribution of this. So again, here what I did is I hid a little bit of the messiness from you on these slides. If you look on the notebook, it shows exactly how I did this. But using pandas type, grouping on clusters, aggregating, I get this cluster level data set, and now I can plot the point of each cluster by the mean asset score. And so what we'll see here is, you've already seen a satellite imagery of Nigeria at this point, and we see that that's, the clusters down here tend to have a lot more assets. As we get into the north, we see, much lower asset scores. For now, what we want to do is we want to try and combine that with the satellite imagery data. So we use raster.io to do this. Again, fairly simple, open command. And as I said, what happens is this is just an image with some metadata, and so we can kind of poke around at what the metadata are. We can look at the coordinate reference system. Life is pretty easy here because our coordinate reference system is the same. We're still in 4326. This is kind of where I say, this is a little bit confusing because 4326 is actually the geographic coordinate. So this is specifying, the shape of the Earth, how we're measuring lat long, and what we mean when we say lat long. But in this case, all we're doing is we're transforming lat long to xy, right? So there's just this direct correlation between lat long and xy, and so that's how we're projecting it. We can also sort of look at the boundary of this image, and so this gives us a bounding box. The thing that's important to recognize is that the units here are going to match your coordinate reference system, and so the units of the bounding box are in degrees lat long. And then we can look at sort of the image size. So this is a massive image. I can't even plot this image on my computer. It will crash. But what we do have is the ability to use this metadata in order to do a mapping from the pixels to lat long. And so we have that connection. And so we can do any sort of calculation we want on the specific area of interest. Okay, thank you. 5 minutes for my talk or 5 minutes until this questions time starts? Yeah, okay, that's great. Okay. Okay, so again, this is sort of the simple way of masking just to look at Nigeria. So all we do is we bring in a polygon of Nigeria, which I just took, the GeoPandas has these sorts of things built in, so you can figure out what that polygon is. And then you mask it. And so all that's doing is it says, just give me the pixels that are inside that polygon, and then I can plot that as an image. And now what we want to do is we want to calculate that for each cluster point. And the thing that's a little bit complicated about this is that a point it doesn't have any intersection, right? It's just a single infinitesimal point, and so you'll get an error. It'll say there are no pixels that are encompassed by this point. And so what we want to do is some sort of buffering operation in order to expand that pixel to a real polygon. And so a buffer is just, pictorially, if we have a line and we buffer it by a distance, we take all points that are within that distance. And so that's what we want to do. We want to buffer this to be a polygon. But there's a little bit of uncertainty here because the way the buffering operation works is it's going to be within that projection system. So if we naively do a buffer, we're buffering in degrees lat lon. And that's not really what we want to do because a degree of latitude or longitude has a different distance across the Earth. So as you go into the northern hemisphere, 1 degree, or further polar, I should say, 1 degree of longitude has less distance than around the equator. And so in order to do this, we do a series of transformations. We transform it into a coordinate reference system that is in meters and has a small amount of distortion in the area we're interested in. In this case, I just sort of Google around and I find this one. So this is a nice one that has small amounts of distortion within Nigeria. And so I transform it into that coordinate reference system. Then I do the buffer by 5,000 meters, 5 kilometers, as I know that that's the amount that this has been anonymized. And now I have a polygon, but now I'm in the wrong coordinate reference system to do my calculations on the nightlights. So what I do is I transform it back. So ultimately what I end up with is a polygon in lat lon that is a constant 5 kilometer circle on the Earth. And so sort of pictorially, if I do this in the center of Nigeria, I get a circle that looks like this in lat lon. But if I do this in Germany, I'm going to get a circle that looks like this in lat lon. But this is actually the same size and shape on the Earth, which is what I care about. And so now, this is sort of in pseudocode how I do this. I define this coordinate reference system. This is my old coordinate reference system. I do these series of projections. And now I do the same thing where I basically am doing a masking operation on the night lights. And then I can calculate the mean value of night lights within that polygon. Then I can plot this as a sort of see the relationship between mean night lights and the median cluster assets. And we see that there's a pretty clear relationship here. People who have very low assets produce almost no night-like activity. And then as you get higher asset scores, then you start seeing a range in activity. If you go to the GitHub repository, I also did this a little bit in the US. It's kind of interesting to see because you see a very clear up and then down. Very wealthy areas in the U.S. actually produce less night lights than other areas. It's kind of interesting to see the variance. So that's sort of it. I hope this was interesting. I hope I kind of convinced you that working with geospatial data is really powerful. The nice thing for us at least, and I'm sure for many other people, is it's quite cheap. I think it's a lot of fun to play around with these things. General guidelines. Just make sure you're matching the coordinate reference systems when you're comparing data. You want to transform to projections that make your calculations easy and accurate. And then when you're dealing with the raster data, you always want to transform your vector data to match the raster data. And then finally, Python really provides really excellent tooling about that. So with that, hopefully I did well enough on the time. How am I looking?
Yeah, you did perfect.
All right,
so thanks a lot for the useful and interesting talk. So we have time for some questions. Any questions? Raise your hand.
All right, I answered them all.
So you answered a lot in your talk, obviously. But one question, did you try? There's a question.
Thank you. It was a very interesting talk. I was also curious about your use or not of tools like QGIS or Leaflet or other things that are maybe more well known to the common people.
Yeah, it's interesting. So I don't know if everybody heard. He was asking about comparing the tooling to QGIS or some of the other tooling that's out there. So in my experience, I think a lot of those tools work great if what you're after is producing really high quality images and things like this, if you want that kind of thing. for the type of work I do, I mean, I work as a data scientist, and so we're interested in sort of trying to do these things as programmatically as possible. And I found that like Python is a really good tool for that. It also mixes really well with the rest of our analytics stack and any sort of calculations we're doing. Leaflet is something else you mentioned. So Leaflet is a good way of doing visualization. So if you want to try and do, like, you're building an app and you want to try and surface these insights to your customers, then this is a good way of going. And there are lots of tools out there, including in Python, to allow you to sort of interface nicely with that stuff as well. Yeah.
Hello, thank you for the talk. It was really interesting. I was wondering if you could tell us how it will be a normal day for you using these tools to solve Apollo's problems.
Yeah, so asking about a normal day. Yeah, so I think, so a lot of what we end up doing is designing. We design a lot of systems to allow us to do things in sort of like a very rigorous way. With it's like things like the school location example, right? So we want to come up with a proxy for location, so we use school location. But then we end up running with problems where you're like, great, well, how do we know school location? So people we do a survey, we ask people, they send us an SMS or something to say where their closest school is, but they're wrong, right? And so now we're like, okay, cool. Actually, that's some really interesting insight for us. We're trying to design a credit product. We want to know, are people who are correct about their school more likely to repay? Does that, or is this fraud, right? So we want to say, okay, cool. Let's. This is now for me as a data scientist, I'm like, this is my thesis. I'm interested to know if there's a relationship between what people say and what's true. And so now I build this I try and build a model on this. So now I'm looking at not just what you say, but I want to know how far off you are. So I calculate what is actually your closest school, and then I say, how far off are you from that? And so now I have this process of saying, some of these can be quite memory intensive, right? To calculate the actual closest school, I have this huge database of tens of thousands of schools. I have to go through them all. And so, you're trying to play these sorts of games about being efficient. But then you can come up with a plot and say, what is the distribution of actual school distance to reported school districts distance for people who repaid their loans versus people who defaulted on their loans? And you play these sorts of games. So.